All right, in this problem, we're going to look at calculating the energy change in a nuclear reaction. So a couple things possible here. One is we can have energy released or absorbed. So how are we going to figure that out? Well, we're going to calculate the exact masses of the products and the reactants. And if we subtract the products from the reactants to get that change in mass, if it's greater than 0, it's absorbing energy. So the products are larger than the reactants. If it's less than 0, it's releasing energy. So that's what we're going to solve for first. And then if we scroll down here, we can see that we're going to calculate exactly how many kilojoules per mole and how many MeVs we get. So let's add them up. So this is a fusion one. So we're small elements fusing together instead of large elements breaking apart. So let's see what happens here. So we got product side, we got just our helium, which is 4.00260. Our reactant side is 2 hydrogens. And 2 neutrons. Okay, so let's subtract. And we get our change in mass is equal to negative 0.0303298. So that is smaller than 0. So energy is being released. So like the sun, right? Hydrogen reacting. So that's an example of fusion, and it's releasing energy. So that's what's going on here. Now this is in AMU. So the first conversion, even though MeV is listed second here, I'm going to do that one first because that one's pretty straightforward. We take our AMU and we multiply it by 931.5 per AMU. And notice I'm not using the negative here. That negative was just showing us that there was a change in mass. So 28.252. Okay, so let's put that in 3 significant digits. There we go. Now let's look at kilojoules per mole. How do we solve for that? Well, we use our E equals mc squared equation. We're solving for energy in kilojoules, and we have mass and speed of light. Our speed of light is 2.998 meters times 10 to the 8th meters per second. Now we're looking for kilojoules. Well, a joule, the units of a joule are kilograms per meter times meter squared over second squared. So you can see if you square that, we're going to get the meters squared per second squared. And so we just need kilograms, and then this is per mole. And so we need kilograms per mole. Well, how do we get this? Well, we learned last term that AMU can also be seen as grams per mole, right? So AMU is 1 atom, 0.0303298 grams per mole. If you have a mole of atoms, it's that many grams. But we need kilograms, so we're going to convert 1,000 grams per kilogram. We get 3.03298 times 10 to the negative 5th. Now I'm going to multiply that by the speed of light squared, and I get 2.726 times 10 to the 12th joules per mole, or kilograms times meter squared times second squared. Now, last step, it asks for kilojoules per mole. So I'm going to say there's 1,000 joules per kilojoule. and we get 2.3 times 10 to the 9th kilojoules per mole. Lots of kilojoules coming from that for every mole of atoms we're working with. So let's type this in. Times 10 to the 9th. And there we go. Okay, so some good math. Going to use that E equals MC squared equation you've heard about all your life and determine if energy is released or absorbed.